Hello, Algebra 3 class. Yes, we are definitely back here in Chapter 8. We're working our way back into the algebra section. We had done the trig for a little while because you absolutely needed to have that trig portion thrown in. We're back here, and the way that I'm approaching this chapter is as if we need to fill in some gaps and also to get you ready for the seniors for their college placement exams, if your college is requiring that to know where you are, or for the juniors getting you ready for SATs when those things will happen. So we're just getting you ready, positioning you to be able to do well with those things. So we're back here with radical expressions. You should remember, or reminding you that a square root is asking you what times itself gives that number. When you put an index in there that is not a 2, it tells you that you need that number of them. So for example, a cube root, you need 3 things multiplied together to give you this. A fourth root, you need 4 multiplied together to give you that. This is our radical sign. The number that's in this little V part is called an index. And right here, this one is an implied 2. And like I say, we're doing this as a reminder to you. So when you're looking for what number is multiplied times itself many times, some of them are ones that you should be somewhat familiar with. So here we're looking for cube root of 64. So you have to find a number that when you multiply it together 3 times, it's going to give you 64. And so you think about things that you definitely know go into 64. So for example, 2, but 2 times 2 times 2 just gives you 8. 3 isn't going to get it, but what about 4? Yeah, 4 times 4 is 16, times 4 gives you 64. So your answer is 4 there. And you do that same process through the others. It would probably be a good idea if you pause it right now and then come back just to make sure that you're right on these, or look at the notes to make sure that you're right. Okay, so this one turns out to be 5 because 5 times 5 times 5 gives you 125. This one turns out to be 2 because 2 times 2 times 2 times 2 gives you 16. This one turns out to be 2 because 2 times 2 times 2 times 2 times 2 gives you 32. This one's interesting because you're looking at a fraction, but you're really looking for what number times itself times itself. 3 of them is going to give you 8/27. So think about them numerator and denominator separately. That's the easiest thing, because 2 times 2 times 2 gives you 8, and 3 times 3 times 3 gives you 27. So your answer is 2/3 here. When you look at decimals, your initial gut instinct should be to think about it without the decimals to get yourself in the ballpark, and then play around with the decimal points a little bit just to make sure that you've got the right one. So for example, this one, we have 0.2 times 0.2, which is 0.04, times 0.2, 0.008, times 0.2, 0.0016, which is your actual answer. Now, if somebody had thought ahead and thought, wait, there's a lot of zeros here, maybe it's 0.02, right in the first 2 multiplyings, you would see that you have too many decimal points and you'd want to dial it back a little bit. Okay, so we have some technicalities and some things that we need to talk about. First of all, you can have an even and positive index. Okay, so if you have an even index and you have, an even index and you have a positive number down here, not even an even positive index, but an even index and a positive number under each, you have 2 possible solutions. You have the positive and the negative value of that. So for example, the square root of 4 could be 2, but it could be -2. If you have an even index and you have a negative underneath the radical, for example, the square root of -4, there's no real number that will work with that. Yes, in your past somewhere you talked about the imaginary numbers, the complex numbers, but for the most part, in most calculations in life, you're looking for real solutions. So right now we just say there's no real solution. So we're not looking for those crazy numbers. Just if you have a square root or a fourth root or a sixth root, any even root of a negative number, there's no real solution. And if you have an odd number, an odd index, there's going to be exactly one correct answer, not more than one. So we've got some examples here so that you see what I'm talking about with those. For example, the square root of 100 is just 10. Okay, nothing crazy about that one, just 10. But when you put a negative outside here, they're implying that you want to have the negative value of that. So here we have 10, here we have negative 10. This one is called the principal square root, and it's the one that usually you are taught first, like way back when you start thinking about what is a square root, they teach you that. But then if they want the negative value, they usually put a negative out front for that. Now here's this other variation on that 100. If you're taking the square root of a negative 100, we have a problem because there's no number times itself that's going to give you a negative, so you have no real solution. For our cube roots here, what number times itself times itself? It's only a positive 2 here. There's no possibility of having a negative answer for that because 2 times 2 times 2 is the only thing that gives you 8. So we don't have like a principal cube root and a negative cube root. You just have a cube root. If they want you to have a negative 2, they'll put a negative out front, but this is still the cube root of 8 is 2. The cube root of negative 8 is negative 2, because negative times negative gives you positive, times negative gives you a negative. There's not two possibilities here, just one possibility. Fourth root of 81, well, because 3 times 3 times 3 times 3 equals 81, we get 3. And once again, if they want the negative version of it, they'll put a negative out front. Okay, so just reminding you of all the things that maybe you knew, but maybe you didn't quite master, but maybe you did master it. And if you did, that's great, and this is just really easy for you. Okay, we want to look at a little bit of the graphing. I have here some numbers that work with this because the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, and so on and so on. You could pick a whole bunch, but they get to be very large and difficult for graphing. So if you were to put these on a graph, you have what looks like a half of a parabola, which actually makes sense. Square root of 0 is 0, so that's actually a point not on here, but it is a super important point. We're not having any negatives here because we can't have a square root of a negative. So we only are looking at the positives, and the perfect squares just give you nice points for graphing. Now we need to think about your domain and your range for this, because as you go up the math ladder, you're going to domain and range become very important. So your domain is all of the x values. We can't have any negative x values because of what I just said. So that means your domain is all of the positive values. Now because there are no negative values left allowed in the x values, the smallest number you would have would be a 0, so you're going to have only positives here. But 0 is allowed, so that gives us our domain and our range. Now there's two different notations for that. Here's our set builder notation. All x such that x is greater than or equal to 0. All y such that y is greater than or equal to 0. But you should know that we also have our other notation. Okay, we also have, oopsies, I need to get to my, we also have this notation. All x starting at 0 going into infinity. Okay, if you remember that notation that we were working with earlier on, this meaning that 0 is included, so 0 to infinity. The y, the range is also 0 to infinity. Just to remind you how to draw that as well, I want to take them and I want to copy, and I'll put that over here. Actually, I can just copy the same one twice, can't I? All right, we're going to go here and I'll paste it. There we go. So 0 to infinity for your domain, and here's another one, 0 to infinity for your range. All right, starting at 0, 0 is included, so it's the boxy looking one, and then the parenthesis looking one to go for infinity. So that's our square root, our basic square root function. And there's quite a number that are important. You know, you've had your parabolas and various different shapes. The sine, the trig functions have their basic shapes for graphs also that are important. And just like the trig functions could get moved around, these can get moved around, which we'll look at shortly. But I want to look at another basic function, which is your cube root function, since this is our lesson today with the radical expressions. Here are the perfect cubes with their cube roots, and when we graph them, what we find is that we have something that looks like this. It's more stretched out than a parabola. 0, 0 is a point, but our domain and our range are both negative infinity to infinity. X can be anything, and you will always be able to find a cube root of it. Now, the thing that's difficult to understand is that the range is also infinite. It's just that it's going to take a lot longer for that range to be increasing and decreasing in value. But negative infinity to positive infinity, your domain determines your range. Okay? All right. Now these graphs can be shifted. So you need to keep in mind your basic shape for your square root function and for your cube root function. And for any of the others, if you start looking at their graphs, as we talked about quite extensively in Algebra 2, but just in case anybody had not quite grasped onto that, is that if you know what the basic function looks like, then you can move it around by manipulating the things that go with the x and the things that are on the outside of the original function. So this one here actually is going to take everything and move it to the right 3. And if you're not really quite clear on that, you can make yourself a table of values. And a key value in here, one that you should always pick, because we said zeros are important. Square root of 0 is kind of like an end to it. You can't really go beyond 0. So 0 is an important point, and then the rest of the graph looks like the original one, but is based off of that. So for example, if I have 0, or if I have 3 minus 3, that gives me 0, and the square root of 0 is 0. That's where that whole shifting to the right comes from. Because if I tried to use 2, what's going to happen? I'll get a negative here and have no value. But then if I try 4, we get the square root of 1 again. Why did I pick 7? Well, 7 because 7 minus 4 is 3, and the square root of that gives me 2. So you're looking for something that has that same basic pattern happening. But really, if you study the pattern a little bit and you know what's happening here, and we have something that's right attached with that x, that's going to affect where that 0 point is and then what happens after it. If you had something, if that negative 3 was on the outside of the radical, instead of moving it this way, it would have moved it down, because you still would have had the square root of 0 at 0 in that case. We'll look at that scenario over here with our cube root function. So our domain, and for right now, what you can do is make yourself a list of ordered pairs, and that'll help you figure out where the graph is. The most important point is going to be the one that the starting point. Okay, so that can always be found by taking a radical and figuring out where that's going to be a 0, and that will help you narrow that down. So our domain now is not starting at 0, the domain is starting at 3. So it's everything bigger than 3 is going to give you a right answer, or 3 itself. The range is going to start at 0 once again and go to infinity. So my range is in interval notation, looks just like it did before. So here's our range, 0 to infinity. But our domain, if we look at that, our new domain has to be starting at 3 and going to infinity. So we have those things to deal with. Okay, you should make yourself able to be adaptable as far as what your context is. And when you take your next math course, wherever that is, whatever it is that you're doing, whether you're going into the college setting or whatever, just be aware of these notations so that you know that you're looking in context and seeing whatever you're doing in class as far as what's appropriate for that class level. All right, so here, once again, if we plug in values, we can find things, and what we notice is that we had that original one that started at 0, but this plus 2 ended up dragging the whole graph up 2. This cube root of 0 is still basically a really important anchor point because it shows where a turnaround happens. So that would be important, and then going up from there and down from there, but your graph has to have that same shape happening with it. Okay, so our domain here, once again, is infinite in both directions, and so is our range. Okay, so the graphing, just a thing that we needed to make sure that we reviewed and went back over. Now there's this little thing that happens. We have to be careful when we have an even root and we have an even power, and then when it simplifies, you get an individual number. We have to be careful of what our answer turns out to be. So for example, the square root of 7 squared. 7 squared is 49. So the square root of 7 squared is just 7. But so is the square root of negative 7 squared. So a square root undoes a square, but if you have a negative here, because this becomes a positive when you square it, then your answer turns out to be a positive of whatever that was. We don't know if this one's a positive or negative, so you put an absolute value around the answer so that you're safe. This one, once again, we don't know if the original was a positive or negative, but if you put an absolute value around it, it turns the answer automatically positive, which, because there's nothing out here in front of these square roots, they want the principal square root, so that involves making sure you're getting the positive answer of it. So nice little technicality so that you are getting appropriate answers. I'm going to bring up another page of examples for you to ponder. Okay, here's our rule. As long as n is even and positive, the nth root of a to the n is going to equal the absolute value of a. If n is odd and positive, then they also undo each other, but you're not doing the absolute value. Because remember, an odd root, like the cube root, can have a negative answer. So we have slightly different rules. The odd ones, you can have a negative come out, or the actual value. The even ones, you're going to end up with an absolute value scenario. So let's look through these examples. You should probably have paused and tried it just to see. So this one is going to be a positive 3, because when you undo the 6th root with the 6th power, or undo the 6th power with the 6th root, all this multiplying would give you a positive answer, so your answer is positive 3. This one, though, is an odd root and an odd power, so we get a negative 4. This one is, this negative out here is not with the 4. The negative is in front of the entire radical. So the fourth root of the fourth power of negative 9 would give you a positive 9, because it's the absolute value of negative 9, but this negative on the outside means that your answer is negative 9. So our absolute value rule works, but you have this extra negative out here to throw into making it negative. Okay, here, this one. Now this one has a nice little trick to it, that if you have an index and you have a power, you can take the power divided by the index, and that'll give you your new number. It's because m squared times m squared, so you're square rooting that, that gives you m squared. It's the absolute value. But here's the thing, because it's an even power, even if this was a negative, it would turn it positive anyway, so the absolute value bars are not needed. I'll say that again. Because you ended up with an even power, even if the m were negative to start with, your final answer is an even power, which will turn it positive, so you don't need the absolute value bars to turn it positive. So your answer can simplify like that. This one is really a to the third to the fourth power, or a to the fourth to the third power. And so then when you cube root the cube, you just get a to the fourth. Okay. And the shortcut is that you take 12 divided by 3 and get 4, because you're thinking about groups of 3 here. Okay, so we've got 4 groups of 3a's here, so that's how that works. Same thing here. We're doing a fourth root of a to the third to the fourth, because 3 times 4 is 12. That gives you a to the third power, but because this might have that nasty negative hiding in it, we need to absolute value your final answer for that one, because it's an even root and we ended with an odd power. So you might want to write that down. If you have an even root and you end with an odd power, that's the only time you really have to worry about those absolute value bars on your variable. Now calculator. Okay, many of you already know how to do at least the square roots. The cube root and the fourth root might be something new to you. We actually can use fractional exponents too, but that's for a different day. Well, I actually have the screens already here for you. Square root of 39, second of this square button, you can see that square root right there. I can make this really big too. See how it's the square root is right above the square, so when you do the second of the square root, what you end up with is finding the square root of that. This gives you your decimal approximation. The square root is there. The cube root and the fourth root are hiding under the math buttons. So if you go under math, oh, I didn't mean to do that. If we go under math, and then you go down here, here's where cube root's hiding, just like on this screenshot here. And then you can put in your number and hit enter, and you end up with your answer, 4.531. Do use the rules of rounding. If it says to 3 decimal places, please round here. Use the rules of rounding. 6 and up comes up. All right. We have another thing, because what if your Okay, so we have our square root, our negative square root. You can put a negative in front of the symbol, and that's simple enough. The fourth root one's the one that's a little tricky, though. The fourth root one, you have to use that in your math section. You can change all the roots, but the sequencing is a little odd with the TI-83 plus. Like if I want to do the fourth root of 39, we do fourth root. I need to go into the math, and here option 5 is my root button. Fourth root of 39, and we'd hit enter. Now if you're wondering, did I get my right answer? Okay, remember fourth root and fourth undo each other, so in order to check to see if you got your right answer, you can take that answer to the fourth power, and if you get your answer back, then you're like, okay, I just did that right, because sometimes it's easy to forget as you're going through how to use different ones of these buttons. This math button, pretty important, because there are things that hide under there, which is very good. So if I wanted to, even if I wanted to take like the 18th root, I could take the 18th root, which would be, oops, I don't want the second. I just want math. And if I want the 18th root, the 18th root of 39. Now this notation bothers me a little bit because it's not really clearly showing that this is an index, but that is what it is on there. So there is that. So if that were multiplied times itself 18 times, you would get 39. So we just checked that. So that example wasn't on here, the 18th root, but you can see you can use that particular function for any root that you want. All right. Hope you're having a good rainy day today. At least it's supposed to be nice the rest of the week. I will right now bid you farewell. Make sure you're getting some things done. Assignment 65, make sure it's ready to turn in tomorrow. And God bless you and have a great day.